Okay, let's do a quick review of Carson's rule. Carson's bandwidth rule gives you the approximate bandwidth requirements for an FM communication system. Here, the estimated bandwidth is BC. Beta is the modulation index, and W is the message bandwidth. Then Carson's rule gives us that the estimated bandwidth BC is equal to 2 times the quantity beta plus 1 times W. For frequency modulation, the modulation index is given by the frequency deviation divided by the message bandwidth. The frequency deviation delta F is just KF times the maximum absolute value of the message signal M of t. Here, KF is the frequency deviation constant. This allows us to rewrite Carson's rule as BC equals 2 times the quantity delta F plus W. Note that both these forms are useful when using Carson's bandwidth rule. Let's look at an example of commercial FM radio. The peak frequency deviation for commercial FM radio is 75 kilohertz. The maximum message bandwidth is given by 15 kilohertz. Then Carson's rule gives us that the bandwidth of commercial FM radio is 180 kilohertz. Compare this to the bandwidth of double sideband AM, which in this case would be 2 times 15 kilohertz or 30 kilohertz. You can see that FM requires 6 times the bandwidth of double sideband AM. Let's look at another example. Let's say we have a message signal that looks like a triangular pulse train input. So it looks like this M of t shown here. This is a periodic signal, and the period t is equal to 2 times 10 to the minus 4 seconds. What we mean here is that the distance of the peak of one triangle to the peak of the next triangle is the period t. The question is, what is the bandwidth of an FM signal that is generated by this triangular pulse train message signal? Suppose that the carrier frequency Fc is 100 megahertz, and the frequency deviation constant Kf is as given here. Let's apply Carson's rule, which estimates the bandwidth of an FM signal as 2 times the quantity modulation index plus 1 times the message bandwidth W. For frequency modulation, the modulation index is given by the frequency deviation divided by the message bandwidth. The FM bandwidth can also be written as 2 times the quantity delta F plus W. Let's first compute the message bandwidth W. Note that the Fourier transform of a triangle is sinc squared. Now recall that repetition in time is sampling in frequency. Hence, the Fourier transform of the periodic triangle is a sampled sinc squared function in frequency. Note that the frequency support of the sinc squared is infinite, which is not very useful. Since the sinc squared drops off quite fast in frequency, we will take the third harmonic as the bandwidth. The third harmonic is 3 times the fundamental frequency, which is the first zero crossing of the sinc squared. The fundamental frequency is related to the sampling rate or the period t. In other words, the fundamental frequency or first zero crossing is at 1 over t, which in this case is 5 kilohertz. Then the approximate bandwidth is 3 times the fundamental frequency, which means the message bandwidth is 15 kilohertz. Now let's compute the frequency deviation delta F, which depends on the frequency deviation constant and the maximum absolute message amplitude. We can see that the maximum message amplitude is 1. The frequency deviation is then just Kf times the maximum message amplitude. You will note that we have a division by 2 pi here. It is here because of the units of kf in the example I took. You will often see this 2 pi scaling in books that use angular frequency, like omega equals 2 pi f, instead of just regular frequency f. Plugging everything in gives us that the frequency deviation, delta f, is 100 kilohertz. Plugging in delta f and w into Carson's rule gives us that the FM bandwidth is 230 kilohertz. We can also ask the question, what happens to the bandwidth if we double the message amplitude so that the maximum absolute message amplitude is 2? Please try this on your own, but you should be able to see that the delta f doubles while the message bandwidth remains the same. So the FM bandwidth in this case is 430 kilohertz. We can also ask the question, what happens if we double the signal period or cut the signal period in half? In both these cases, you should be able to see that delta f remains the same, but the message bandwidth will change proportionally. With double the message signal period, the message bandwidth is cut in half, giving an estimated FM bandwidth of 215 kilohertz. With half the message signal period, the message bandwidth doubles, giving an estimated FM bandwidth of 260 kilohertz. These examples show you how to use Carson's bandwidth rule to estimate the FM bandwidth for a given message signal.